Hey everybody, this is Miss Eisencraft here with Unit 2, Lesson 10, Practice Problem Help. Okay, let's just jump right in. Andre bought a new bag of cat food. The next day he opened it to feed his cat. The graph shows how many ounces were left in the bag on the days after it was bought. So we have a graph here, looking good. All right. Okay. First question, how many ounces of food were in the bag 12 days after Andre bought it? So I'm going to go to 12 days on my graph here. Okay. And then I'm going to go up. Now it's a little bit of a tweener. Oh dear. So what do we do there? Okay, so if it's a little bit of a tweener, what you can do is you can take some nice numbers that we know, like 56. And by nice numbers, I mean where they fall on the grid nicely. Okay, so I'm just going to go like this. This will help us later. I'm going to take days and then ounces of cat food. Okay, on day 0, there was 56. I'm going to leave a bunch of space. Day 24, there was 16 ounces. Okay, so it looks like that's a decrease of 40 ounces in 24 days, right? So we could probably take half of that and say, well, in 12 days, the cat would do half as much. The cat would eat half as much. So that'd be a decrease of 20. So I think 36, and that looks about to be 36. You might say, well, I just took half, but sometimes you have to be careful because you're not sure if in between means necessarily exactly half. So I'm going to put 36 there. Okay. How many days, hopefully these are a little more straightforward, how many days did it take for the bag to contain 16 ounces of food? So I'm going to go to 16 on the ounces, go to 16 ounces, right? And then go over here. Hey, we already found that. That was 24 days. Fun. How much did the bag weigh before it was opened? Well, that would be day 0. It weighed 56 on day 0. Go up to here, 56 ounces. And then about how many days did it take for the bag to empty? You can go over here. You know it's between 32 and 36. You can figure out, well, how much is that per day? But we can just say roughly it looks like 34 days. In the middle, 33 might be about right. But we're just going to say, because it says about, we're going to say about 34 days. We could continue our table, but we just really want to inspect the graph and see if we can use the graph to answer that question. All right, let's keep going. Question 2, another graph. A Little League baseball team is ordering hats. This graph shows the relationship between the total cost of the hats, yes, over here on the left, in dollars and the number of hats ordered. What does the slope of the graph tell us? So it doesn't ask for the slope, but if you recall, and we're going to talk about this a little bit more, slope is basically we've heard of the term rise over run, but you're asking how much does the cost increase every time you order another hat? Or how much does the cost increase after you order a bunch of hats? Okay, so slope we often hear as change in y over change in x, or the change in the cost for every hat. And the cost, it looks like, is going up every time we increase hats to the right. So even though these things might be true, some of these other things might be true, the slope is telling us the amount that the total cost is increasing for each additional hat. So when you simplify the slope, you're finding the increase of total cost per hat. All right. Okay, let's keep going. Question 3, a group of hikers is progressing steadily along an uphill trail. The graph shows their elevation or height above sea level in feet at each distance from the start of the trail. Okay, so I'm taking a look here. We are starting at time 0. You start with an elevation of 500 feet, and then as you go more and more miles, your elevation is going higher and higher. So the slope, And if you recall from middle school, a slope is really easy to find if you find two nice spots on the graph, okay? And you take the rise over the run. So this looks like it's increasing by 500 feet every 2 miles, okay? Now we can simplify that. That is slope, but simplified, it'd be 250 feet every 1 mile. So I'm going to take this is the slope, okay, number one. Number one just says, what is the slope? 250. We don't even need the labels there, and it's 250 over 1 if you'd like to make the slope a fraction. Number two, what does the slope tell us? Just use the labels. You can say, you are increasing 250 feet in elevation every mile. All right. Or you could flip that around and say every mile on the trail, your elevation goes up 250 feet. I like to say y over x. Okay. 3. Write an equation that would represent the relationship between the hiker's distance from the start of the trail, x, and their elevation, y. So this is an example where an equation would be easy to write in slope-intercept form. And we're going to talk more about this on day 2 this week, but slope-intercept form is helpful when you have a nice starting point, and then you know what if something is increasing or decreasing. Okay, so we know we are starting at 500 feet, and then we're going up 250 feet every mile that we go on the trail. You can always switch these around as long as your slope stays with your variable miles. This is often referred to as slope-intercept form because this equation showcases like the starting point and then how much it's increasing or decreasing per, in this case, mile. So I'm going to go ahead and type that in. Y equals, it doesn't matter which way you choose it, 250x plus 500. Number 4, would it make sense? Does the equation y minus 250x equals 500 represent the same thing? So I'm going to think about what we talked about the last couple weeks about equivalent equations. I could solve it, right? And see if they have the same solution. Or I could say, hey, is it legal to just move that 250x over? Well, you could take your total height and subtract 250 from every mile. That's like going backwards on the hike. So if you started at 500 and then you went backwards, this is also an equivalent equation. You would get the same solutions. So yes. Oopsie. Yes. The equation is equivalent. It has the same solutions. We also got it by subtracting 250 from both sides, which is an allowable math move. All right, a kindergarten teacher bought $21 worth of stickers and cardstock for his class. The stickers cost $1.50 and the cardstock costs $3.50 per pack. Here's the equation. $1.50 per sticker plus $3.50 per cardstock equals 21. How can we tell that this graph represents the situation? Well, one way you can tell is that every spot here labeled on the graph, okay, every spot needs to be a solution. So I'm not going to go through there, but that would be one way that you could tell. If you wanted to check if it was right, you could check those numbers like 0, 6, and then you could check 7, 3. And all of these should always add up to the $21 if it is the correct graph. So one way to tell is the points or the coordinates on the graph would work in the equation. They would all make the equation equal 21, and they do. Number 2, the sticker, what do the vertical and horizontal intercepts 0, 6, and 14, 0 mean in this situation? So one way I like to write this is 1.5 S is stickers plus 3.5 C. So they're asking what 0, 6 means. So if you plug 0 in there and 6 in here, okay, that gives you the solution 0, 6. And what that means, if you really interpret it, is if you got 0 stickers, how much cardstock could you buy to spend the 21? So it's kind of the extreme. Like, what if you zeroed this out? If you zeroed out the stickers, you could afford 6 pieces of cardstock or 6 packs of cardstock, for $21. So 0, 6 is like an extreme. I like to kind of think of it this way. Stickers, cardstock. If you bought 0 stickers, you could afford 6 packs of cardstock. And 0 is a nice number to calculate with because if you go the other way, 0 is just nice because it, kills the term. The other, we call this an intercept because it is intercepting the axis. What if you got 0 packs of cardstock and you were just totally into the stickers, so you didn't spend any money on cardstock? How many stickers could you afford? And it looks like 14, and that would spend the total $21. So 0, 6 that's a comma, means you could purchase 6 packs of cardstock if you didn't get any stickers. And the other one, 14, 0 means you can purchase 14 stickers. I believe they're, stickers if you did not purchase any cardstock. So they're like the extremes in this situation. And usually there's something in between, which is the real solution. But these extremes are really helpful because they're easy to calculate. And you really only need 2 points to make a line. So oftentimes it's a really good strategy to find those extremes called the intercepts to make the graph. Okay, let's keep going. Okay, that was question 2. Okay, here we go. All right, a rearranging equation. In physics, the equation PV equals N times R times T is the ideal gas law. All right, we don't need to even understand what this really means. It just says which equation is solved for T. So solve for T means get T alone. PV equals N times R T. If we want to get T alone, it looks like T is being multiplied by N times R. So let's divide by N times R. Think of that as just one number. I know it's weird, but T is equal to P times V divided by N times R. All right, do I see that over here? I do. Okay, 2 more questions. More rearranging. Consider the equation 3a plus 0.1n equals 123. Let's solve for n. This one is pretty straightforward until the end. Something a little weird happens. Okay, we are going to try to get n alone. So we're going to subtract 3a. Even though we don't know a, it's no big deal. We just write the expression. Now we need to divide by 0.1. Now, when I first look, I didn't see this anywhere, and I'm like, uh-oh. That is because sometimes this number at the bottom can simplify, or I'm sorry, this whole expression can be simplified because you can divide this number into both of these terms. So one way I like to write it is when there's a big division bar, this bottom number needs to divide into both. You can often leave it like this, but sometimes that's unsimplified. So what they really did is they divided it out. 0.1, gets divided into both. Think of it like similar to the distributive property, but with division. So if you divide 1/10 into 123, you're going to get 1,230. And if you divide 1/10 into 3a, you're going to get 30a. So although this is often how we will leave it in class sometimes, you can also simplify it by dividing this term in here. And we're going to talk about this more on day 2. Boop. Last one. Okay, Diego's buying shrimp and rice to make dinner. Shrimp is $6.20 a pound and rice is $1.25. He spends $10.55. So right here we have, last problem, we have 620s, yes please, plus $1.25 times R equals 10.55. Okay, so then what we're going to do is we are going to, it says, write an equation that would help us find how many pounds of rice he could buy if we knew how many pounds of shrimp. So we are going to take away 620 times S, $1.25 times R equals 10.55 minus the cost of the shrimp. Then we're going to divide that by $1.25. Because that money is how much is left, but each pound of rice is $1.25. So when we type into Canvas, we're going to have to use parentheses up here. All right. So the rice is equal to total cost minus the cost of the shrimp. I'm going to put that in parentheses because we want all of that divided by $1.25. All right. Okay, guys, hope that helped. Good luck.